Hi, folks. Today we're going to talk about point set topology. Now, topology is kind of an extension of set theory, but it leads to much bigger things. It's one of the most fundamental structures in mathematics. And understanding it shouldn't be too bad, but it can get a little tricky at times. And so topology is a branch of math that tried to bridge the gap from set theory to calculus by skipping over all of that unnecessary geometry. At an introductory level, it is only a little more challenging than set theory, but it quickly escalates to levels far beyond calculus. That said, we should be able to understand the fundamentals without too much trouble. It's sets of sets. That is really all that topology is. And so a topology is a mathematical structure, and the field of topology explores what you can do with it. When we think about how old this branch of math is, it's fairly newer. Most math that we deal with on the daily is really ancient, going back to old school algebra and geometry. Topology only dates back to around 1736. And we'll talk about the initial problem, Euler's seven bridges of Königsberg problem, when we talk about graph theory later. I often think of it as a way of analyzing geometric structures without the geometric tools, and we'll see why. It's a way of understanding the shape of things without exploring what geometric shape you're dealing with. And here's a note on topology. Topology as a branch of study can get very, very challenging at the higher levels. But some of the cooler structures also occur at those higher levels. And we can see visuals of what some of these things look like. Well, we're going to consider what we're introducing here as topology light. We're going to simplify the language a little bit to make it so that anyone can attain an understanding of these shapes. If you want a full course on topology, then you might have to pursue a math degree. These are structures which you can introduce to a child. But at the higher levels, they can get very, very messy. And usually that's where they're studied. And so let's introduce point set topology. A topology on a set X is a collection T of subsets of X, which have the following properties. And so before we even get into the properties, this is just a collection of sets. And so we're talking about some big set X, and the topology is just a collection of subsets of X. And so the properties which we have to have for a topology, we have to include the empty set, and we have to include the whole set. And so the empty set and the whole set, they have to be a part of our topology. The union of elements in any subcollection of T is in T. And so if we have other elements in our topology, we need to make sure that all of the unions of those elements are also included in our topology. We also have to have the intersection of any finite subcollections. And so the unions and the intersections of subsets must also be in our topology. A set X for which a topology T has been specified is called a topological space. Now we have some visuals here of what topologies might look like. Let X be a three-element set, and so X is equal to A, B, C, where A, B, and C are just random elements. There are a lot of different topologies that we could have, and here are some of the examples. This first one, this is saying if we just take a topology which has the whole set and the empty set, that is a topology. If we create a set which has the whole set, the empty set, and then we're going to have a set which is just A, and a set which is AB. Well, we included the empty set, we included the whole set. If we take any unions of A and AB, well, the union of that's going to be AB, which is in the set. If we take the intersection of A and AB, well, that's just A, that's in the set. And so this would describe a topology. All 9 of these are different topologies just on the set ABC. And so this is a type of structure which pops up a lot. And it's just about the most basic structure that we can apply to any type of object. Let's see if we can talk about some examples. And when we're dealing with finite sets, it's actually pretty painless to find them. And so here's a set. We're going to let X be 1, 2, 3, 4. And we're considering a possible collection of subsets T, which is the empty set. 1, 1, 2, 1, 3, 1, 2, 3, and 1, 2, 3, 4. And we're being asked to verify that this is a topology. Well, we have three properties we have to verify. The first, the empty set and the whole set must be included. And in this case, we have the empty set, and we have 1, 2, 3, 4, the whole set. And so the first property definitely satisfied. The next is if we take the union of any two or more elements, we get an element in the set. And so we can really just focus on any pairs because any three would come from pairs. If we do 1 with 1, 2, we get 1, 2. If we do the union of 1 with 1, 3, we get 1, 3. If we do the union of 1 with 1, 2, 3, we get 1, 2, 3. If we do the union of 1, 2 and 1, 3, well, then we get 1, 2, 3. If we do 1, 2 and 1, 2, 3, we get 1, 2, 3. If we do 1, 3 and 1, 2, 3, we get 1, 2, 3. And so the unions of all of any pairs of elements in this topology are also included in this topology. And so you can check the unions of anything in here, it's still going to be in this topology. The last thing we have to check is the intersections. And so if we take the intersections of any two or more elements, are we going to get an element in here? And so the one that strikes me is 1, 2, and 1, 3. If we take the intersection of 1, 2, and 1, 3, we're left with 1. And we have a set which is just 1. And so that intersection is in here. If we do 1, 2 with 1, 2, 3, we get 1, 2. If we do 1, 3 with 1, 2, 3, we get 1, 3. If we do the intersection of 1 with any of these other sets, we're just going to get 1. And so all of the others seem to be in here as well. And so if we take the intersections of two or more elements, we're getting some other set which is in this collection. That's all that a topology is. It's just a collection of subsets of some set. And so it's a set of sets. And in our set of sets, we need to make sure we have empty set and whole set. We have to make sure all unions are in there. And we have to make sure that all intersections are in there. And so this is definitely a topology. Here's one which is not. And so let X be equal to 1, 2, 3, 4 again. And now we're going to consider this set. And so it's 1, 1, 2, 1, 4, 1, 2, 3, and 1, 2, 3, 4. When we look at this, the empty set and the whole set are definitely included. We can take the intersections of two or more things, and we have no issue there. I mean, 1, 2, and 1, 4 is going to give us 1. 1, 4, and 1, 2, 3 gives us 1. The issue is going to be the unions. And so in this case, if we take the union of 1, 2, and 1, 4, well, that's going to give us 1, 2, 4. And 1, 2, 4 is not in this set. And so because we have a union, which is not included in this set, this is not a topology. We would need to either have 1, 2, 4 included in here, or we would need to not have the 1, 4. Either way, it would make it a topology, but as it stands, this is not a topology. Here's a practice problem. If you'd like, pause the video and give it a shot. And so we are considering the set X, which is 1, 2, 3, 4, 5. We know we have the empty set. We know we have the whole set. Then we have 1, 2, 1, 2, 3, 3, 3, 4, and the whole set. I think where we might get into trouble is when we're dealing with this 3, 4 term. Let's see if we can figure out why. Oh, it fails property 2 because of that 3, 4 term. And so if we do 1, 2 union with 3, 4, we are going to get 1, 2, 3, 4. If we do 1, 2, 3 union with 3, 4, we're also getting 1, 2, 3, 4. But when we look, 1, 2, 3, 4 is not one of the sets included in our topology. If we removed the 3, 4 term or included a 1, 2, 3, 4 term, then we would have a topology. But without that 1, 2, 3, 4 term, it's not a topology. We don't have the unions of any sets in here included in our set. Here's another example. If you'd like, pause the video, give it a shot. And so here we have the empty set and the whole set. We have 1, 2, we have 1, 2, 3, we have 3, 4, we have 1, 2, 3, 4, and then we have the whole set. Looking at it, it looks like we might have some issues with intersections. Because if we take 1, 2, 3 and do the intersection of that with 3, 4, well, that intersection is going to be the element 3, which was the set I removed. And so that's going to be a bit of a problem. And so in this case, it fails property 3. 1, 2, 3 intersect 3, 4 gives the set 3. And so we would need to have 3 in this in order to make it a topology. There's a couple of common topologies which we will see, and one of them is based on the power set. If you recall from set theory, the power set is the set of all sets, or all subsets, I should say. And so if we consider the set 3, 4, 5, then the power set is going to be the empty set. It'll be 3, 4, and 5. It'll be 3, 4. It'll be 3, 5. It'll be 4, 5. And then it'll be 3, 4, 5, which is the whole set. Well, the power set always contains the empty set, and it contains the whole set. And any unions or intersections are also going to be included in this. And so the power set is always going to form a topology. We call this the discrete topology. And so the discrete topology is basically the collection of all subsets. This set is often too big to play with. I mean, in this case, it only has a handful of elements, and so it's nice. But if we were to have a million elements, or maybe uncountably many elements, we might not be able to use that set very effectively. On the opposite end of things, given a set X, we can define a topology with just the empty set and the whole set. This is also always a topology, because if you take the union or intersection of the empty set and the whole set, well, you're either getting the empty set or the whole set. This is called the trivial topology. While the discrete topology is often too big, the trivial topology is often too small. Topologies like the ones we've seen in previous examples, well, there we have smaller numbers of elements and we can actually use them to do some interesting things. Because we often have too many elements in a topology, though, we'll usually try and break it down into some smaller set. And we call that smaller set the basis of a topology. And so given a set X, a basis B is a collection of subsets of X which describes a topology. Basically, these are the base elements of a topology, and then we can just take all of the unions and intersections that arise from it and get all of the possible elements for a topology. And so the subsets in a basis are called basis elements. Given a set X, for B to be a basis, it must satisfy two conditions. The first one, for every X in X, so every element of the set, there must be at least one basis element which contains X. And so that means every element of a set must be included in at least one base element. Then if X belongs to two base elements, then X must also belong to a base element contained in the intersection of those first two base elements. And so we have to make sure that our basis includes those intersections. Here's a practice problem. Let X be 1, 2, 3, 4, and we're going to let B be equal to 1, 2, 2, 3, 4, and 4. We're asked to generate the topology described by this basis. This means we want to list out all of the possible subsets of this topology, meaning we want to take all of the unions and intersections of this set, and also include the whole set and the empty set. If you'd like to give it a try, pause the video and give it a shot. As for how we find this, we really just have to list them all out. And so we know we have the empty set, and then we have the whole set, which would be 1, 2, 3, 4. And then we have all of these elements. And so 1, 2, 2, 3, 4, and 4 are also included. And then we have to go through and find all of the unions and if there's any intersections that arise. Don't think we'll have to worry about the intersections. But in this case, we have 1 union 2 is 1, 2. 1 union 2, 3, 4, well, that's the whole set. 1 union 4 is 1, 4. If we are doing 2 union 2, 3, 4, that would be just 2, 3, 4. 1, 2, and 4 is definitely going to be in there. And so 1, 2, and 4, the union of all 3 of those. If we do 2 and 4, that's another one we would need because the union of 2 and 4 is not included in there. And I think that gives us all of them. And so this is our set now. If we want to double check for intersections, I mean, looking at our new elements, 1, 2, and 2, 4, the intersection of that would be 2, which is one of our base elements. 1, 2, and 1, 4, the intersection would be 1, which is one of our base elements. And so it looks like we have all of the members of this topology now. Note that we include the empty set and the whole set, all members of the basis, and then any unions and intersections that come from the members. Yep. Here is another example. If you'd like, pause the video and give this one a shot. Let's take a look at it. And so in this case, we have 1, 2, 3, we have 3, we have 3, 4, 5, 6, we have 7, 8, 9, and we have 10. We're going to have a lot of unions that are going to take place in this. And so looking at this, we have the empty set, we have the whole set X, we have all of these elements. And so 1, 2, 3, 3, 3, 4, 5, 6, 7, 8, 9, and 10. Those are all of the elements we started with. We then have to look at the union of all of the elements. And so 1, 2, 3, and 3 does nothing. 1, 2, 3, and 3, 4, 5, 6 gives us 1, 2, 3, 4, 5, 6. We then have 1, 2, 3, 3, 4, 5, 6, and 7, 8, 9. Well, the combination of those three is going to give us 1 through 9. We could then do 1, 2, 3, 3, 4, 5, 6, and 10, which would give us, let's see, where is that one? 1, 2, 3, 4, 5, 6, and 10 would give us this one. Then 1, 2, 3, 7, 8, 9, and 10. Then 1, 2, 3, and just 10. So 1, 2, 3, and just 10. And that covers everything which includes the 1, 2, 3 term. We then have the 3, 4, 5, 6, 7, 8, 9. So 3, 4, 5, 6, 7, 8, 9, the union of these two. We have 3, 4, 5, 6, and 10. We have 3, 4, 5, 6, 7, 8, 9, 10. So that would be all three of these. Then we have the 7, 8, 9, 10. And then we also have the 3 element. And so we could do the 3 with the 7, 8, 9, the 3 with the 10, or the 3 with the 7, 8, 9, 10. There are a lot of elements. And again, these topologies can get quite huge, which is why we usually use a basis to describe them. If we don't have to describe every single term, a basis is usually sufficient. And so, yeah. Topologies on infinite sets can get a little bit more complicated. And so when dealing with infinite sets, we can't list all of the elements. And so we need to come up with a clever basis for each set. And And so if you recall, the real numbers are the set of numbers which includes all rational and irrational numbers. We have a symbol, which is this funny looking R. It includes numbers on the number line, including fractions, pi, and everything in between. We can describe a number of topologies on the reals, but when we do, we want to use a basis to describe the collection of sets. And it turns out a lot of these bases end up being the same, and we'll talk a bit about that. Our main topology that we use on the real numbers is the standard topology. And so let X be the set of real numbers R, and let B be the set of any open interval AB. And so X is real numbers between A and B, not including the endpoints. This is a basis for a topology. And so we can take the collection of all open intervals and then take all of the unions and all of the possible intersections. And this will generate a topology on the real numbers. If you're ever dealing with the real numbers and no other topology is specified, you can usually assume we're talking about this standard topology. This topology includes all open intervals and unions of open intervals. This topology does not include points or closed intervals. And so it's just a whole bunch of open intervals everywhere on the real numbers. Now, if we want, we can prove that this is actually a basis. And so recall, we have two things we need to make it that this is a basis. One, for every x in x, there must be at least one basis element which contains the little x. And so in this case, if you are a real number, then there's going to be an open interval around you included in this basis. There's going to be an infinite number of open intervals around any value. And so every value is repeated in this basis infinite number of times. We don't have to worry about one. For 2, if x belongs to 2 base elements, then x must also belong to a basis element contained in the intersection of those 2 base elements. Well, we can think of any infinitesimally small interval around x. And so if you are some real value, which is included in 2 separate base elements, we can just choose a tiny interval around that point, and it will be included in this topology, or in this basis. And so this basis of all open sets is itself a basis of a topology. We can also apply this topology to other sets. And so let's say that we want to restrict everything to the interval 0, 1. Well, we can let B be the set of all open intervals AB, which are included in X. And so basically we're saying that this set is going to be the set of all open intervals on the interval 0, 1. And so some examples would include 1/8 to 3/8. That would be included. And so 1/8 to 3/8. 1/4 to 5/6. That would also be an open interval included in this basis. Or we could go irrational, 1/pi, 1. That is also going to be included in this standard topology. This topology itself would include all the unions and intersections of such open intervals. And so this is a topology which describes the interval from 0 to 1. And we can apply this to any open subsets of the real number line. Now let's go on to R2. And so when we think of the number line, we think of it as the real numbers, and we use the symbol R. When we think of the set of all ordered pairs, x, y, we think of it as the Cartesian coordinates. And so the first value is the x value, the second value is the y value. And the symbol we use is R2. And so the funny looking R with a squared symbol next to it. If we wanted to deal with higher dimensions, we have R3, which is the set of all ordered pairs with 3 values. And we can also go higher if we want to. I mean, if we want to talk about 4-dimensional or 5-dimensional objects, we can do that. The math isn't that hard. Instead of having ordered pairs with 3 values, we can make ordered pairs with 5 values, and that would give us R5. Usually, when we talk about things in higher dimensions, though, we are not talking about space dimensions. Instead, it might help to think about it in terms of populations. And so X is a population of something, Y is a population of something, Z is a population of something. Uh, in this case here, here's a five-dimensional system, an ecology. And so in ecology, suppose we have a system with populations of rabbits, mice, wolves, deer, and antelope. Well, we could represent this using five dimensions, R, M, W, D, and A, to represent those five different populations. Whenever we're talking about higher dimensional math, this is what we're talking about. We're not talking about living in some space-time, which is 27 dimensions. We're saying that we have 27 different populations which we are analyzing. Unless you're dealing with high-end physics, in which case you might be dealing with that many space dimensions. But for most, we're focusing on populations of things. And so topologies in these dimensions. The standard topology on R2 is just a collection of open circles. And so let X be the set R2 with values represented by points X, Y, and let B be the set of all circular regions, and so the interiors of circles in the plane. B is a basis for a topology. And so when we look at this, this is a handful of circles. If we take the collection of all possible open circles, well, we are going to cover every single region in R2. And this is the standard topology on R2. Essentially, every single region can be covered by some circle like this. It turns out if we used the interior of rectangles instead, it would describe the exact same topology. And so it does not matter which one you choose. And this should highlight that for a given topology, we can have multiple ways of writing the basis of that topology. We can extend this idea to topologies for Rn for any n. If you're talking about three-dimensional, well, then it's going to be spheres, which are open. If you're talking about 4 or 5, we have to go with some type of Euclidean norm, which means we're going back to what a circle really means. Circle is all points which are within some radius. And so when we're talking about higher end topology or higher dimensional topologies, we could either use rectangles or cubes or whatever dimension we want of a rectangle, or we can go with some form of sphere in higher dimensions. We can also restrict this to smaller intervals, just like we did with the number line. And so if we want to think about the region of x values on 0, 1 and y values on 0, 1, we get this square. This square is sometimes called the Cartesian product. And so if we're thinking of the interval from 0 to 1 in the x direction and 0 to 1 in the y direction, we get this square of values here. We can describe this set or this region using the standard topology. And so just the collection of all possible circles on this region. Every value on here is going to be within at least an infinite number of open circles. And so our standard topology works on subsets as well. Our final thoughts. An important question to ask at this point is why? Why do we care about this? And honestly, that should be a question you ask a lot. There's math for math's sake, which is pure math, and it's a great thing to study. But when we think about topology, it turns out this is the base structure of most mathematics. It's the structure which can describe just about any object out there. And so it turns out when we describe objects, their structures are rarely exactly points on a plane. When we think about the universe, for example, the universe would be really great if we were just living in 3 dimensions and if we were just X, Y, and Z and everything were nice in that way. But we know that space and time are kind of connected. And that connection makes it so that when you're dealing with things in physics, things don't work nicely if you're going close to the speed of light. And you get some really weird behavior around things like stars or black holes, or if you're traveling through space, which we are all traveling through space. And so, yeah, using topology, we can find ways to generalize things. We can stretch things around and deal with spaces which are a little bit stretched. When we think of a triangle, we've mentioned before that there is no such thing as a triangle in the real world. Everything's just a bunch of atoms which are moving around real fast. Well, topology says, yeah, it's close enough to a triangle. And in being close enough to a triangle and having a similar structure as a triangle, we can then treat it as though it is a triangle-like object. And so topology is an amazing tool for describing structures which might not be so nice. And most of the structures we encounter in the real world are not nice structures. I did put a note here, beware, to a topologist, there's no difference between a donut and a coffee cup. And here's the visual to show that. And we will explain how we can turn a coffee cup into a donut very soon. With that, I'll let you get to work exploring where you find topology in the real world. Good luck, folks.